Okay, so in this module, what we're going to do is do a quick overview of the different kinds of t-tests that are out there. Then in the next video module, what I'll do is give you examples of how t-tests are written up in the literature. And then if I have time, what I'll do is actually do a third video looking at SSD4R and how t-tests are shown in the printouts and how to interpret them. So let's start with just a general overview of t-tests so that you understand the statistic itself. So what is a t-test? A t-test, really the most common question that we're answering is the difference between two means statistically significant? And the different kinds of t-tests that can be calculated really are distinguished by how the means are computed and how the variance is estimated in the test. And some of that is just really too much detail for you. Okay, so what I'm going to try to do is just trim away a bunch of stuff that we'd cover in a stats class and just give you the basics so that you understand really the purpose of the test more than anything else. So if the difference between the means is large enough, and by the means I mean here sort of the mean of a control group and a mean of a treatment group. If the difference is large enough, then we say that the difference is unlikely to be due to chance or measurement error, and if that's the case, then we reject the null hypothesis, and we'll come back to that in a moment. So there are different kinds of t-tests. The t-test that you would learn first in a statistics course is a single sample t-test. And in a single sample t-test, what we're doing is we're comparing the mean of a sample using data that we have collected to a known population mean. So the known population mean is essentially the mean of a comparable group in the population that we have already had data collected for us. So, for example, we could compare the mean income of a sample of Winter Park residents, and this would be a sample that we collected as part of our experiment, to the known national mean income that was collected, say, by the U.S. Census Bureau. Okay, so that's data that was collected elsewhere. It is a relevant population to us because what we're trying to do is ask the question, do Winter Park residents make more than the average person? So that would be a single sample t-test because we're collecting one sample, a sample of Winter Park residents and their income. The second type of t-test is called an independent samples t-test. And that's when you compare two independent groups. Now by independent we mean that they're not related to one another in any ways. And so the most frequent case is when we have one group being the control group, which represents, which stands in for essentially the population as a whole, and the other group is the treatment group, and that's the group that receives some sort of intervention or some sort of treatment that is designed to change their behavior or change an outcome. Okay, so the control group is the untreated group, the treatment group is obviously the treated group. And then there's a third set of t-tests referred to as dependent t-tests, and they include just the straight within subjects dependent t-tests as well as what we call a matched samples t-test. So in a dependent within subjects t-test, this is the closest analogy that we have to say an A-B design in single subject design. Okay, so they're the closest. The big difference is that you're dealing with groups of people here, but it's within subjects because the same person is tested once without the treatment and then once with the treatment, in which treated are compared to the scores for when they weren't treated during the control group. And it gets a little complicated than that, but I'll explain it more in just a bit. So basic point, it's pre-post testing of the same subjects, and so we're calculating a different score between the pre and the post-test score within subjects. Okay, and then in the second case, in a matched samples test, t-test, what we're doing is we're comparing the means of groups where the subjects are different, right? Maybe one group gets a treatment and one group doesn't. Okay, now there are different subjects in each group, but they've been matched on an important variable of interest. And so, for example, we might match people in terms of their age. So if I have a 27-year-old in the control group, I match that person with a 27-year-old in the treatment group. And then one person gets the control and then one person gets the treatment. Now, why would you want to match? The reason you'd want is to eliminate a potential confounding variable for the results. So if if the two groups, control group and experimental group, are matched on age, then the mean age for the two groups will be exactly the same. And if the mean age for the two groups, for the treatment and the control group, is exactly the same, then age cannot account for any differences in treatment effects that we're interested in. So both of those examples within subjects t-test and then a matched samples t-test, those are both types of dependent t-tests where the groups are related to each other in some way. Okay, so let's go back to the single sample t-test. Here's what would happen. So we're talking about Winter Park residents, comparing them to the National Census Bureau data. So the first thing that would have happened is that I would have had, or I wouldn't have done it, but the U.S. Census Bureau would have collected data on the population looking at income. And then the Census Bureau will report, okay, so that would be mu. So we take the Greek symbol mu, and we say, okay, the mean in the population would be right here for income. And that's from the extant source, data source, meaning the data source is out there away from us. Okay, it's collected by others. And then I'd have a bell-shaped distribution around that, which should look familiar to you from your glorious days in statistics in the past. And it says distribution in the population for the comparison group is known, not estimated. Okay, why is it known? Because we've sampled pretty much everybody. Okay, now to be fair, U.S. Census Bureau data really is still a sample because we don't really measure everybody, but it's such a big sample that it really kind of stands in for the population as a whole. So for all intents and purposes, we're going to consider that to be equivalent to population level data. But we're not done there because we need to collect the data for the Winter Park residents, right? So we'd have, when we collect the data for the Winter Park residents, we would be able to aggregate the data, calculate a sample mean, and we would let that sample mean represent the population mean for all Winter Park residents, provided the sample is of strong enough quality and integrity and so forth. It's not biased in any way. So we might find that the mean for the Winter Park residents is about here, the mean for the population is about here, and then there's a difference, right, between those two means. The Winter Park folks make a little bit more money than the rest of the country, and we would say, look, there's been a mean shift, okay, meaning that the mean for the Winter Park has shifted over to the right, indicating greater average income. The distance between these two vertical lines eventually gets computed into what we call the effect size, or D, right? So we would express this difference in D units, meaning standard deviation units. And so if we said, okay, the Winter Park residents are 0.5 standard deviations above the rest of the population, that's what these two distributions would look like. My mouse here is messing up on me. There we go. Okay, so what is an independent samples t-test? Well, it's a similar kind of situation. Again, it's the most common question that we ask in statistics: is the difference between two means statistically significant, especially when we have a control group and a treatment group. And so in this case, here's where the big difference is. We don't have access to extant data. We actually collect the data for the control group. And when we do that, what we end up doing is estimating what the population mean is, and then estimating what the population variance is, all of things that are important to know to compute the t-test. So in this situation, we're actually collecting data both for the treatment group and for the control group, and then making estimations of population parameters. Any difference between the means is again reflected in the effect size. But the big difference between a single sample t-test and an independent samples t-test is that the experimenter is collecting data for both the control group and the treatment group. The subjects in those groups are not related to each other in any way, and that's why they're independent. So independent samples t-test. Okay, so it's the most familiar case, and if we would go through and do a study, a controlled study that uses an independent samples t-test, we'd go through a few steps. Okay, and the first step, step one, is to assume that the null hypothesis is true, that there is no relationship between, for example, a treatment and an outcome. So let me give you an example of how that might work. Let's say that I've developed subjects with cancer who took that pill versus subjects with cancer who did not take that pill. Okay. I would assume from the outset that the null hypothesis was true. And what that means is that the subjects who took the pill, the null hypothesis would say individuals who are treated, who received the treatment condition, at the end of the treatment, there should be no effect of that treatment. Therefore, the mean on the dependent variable for the untreated population should equal the mean on the dependent variable for the treated population. Now, that dependent variable could be any of a number of things. It could be, for example, that the independent variable is number of symptoms, cancer symptoms that the person has at the end of treatment. It could be mortality rates. It could be any of a number of things. Okay, but the main point is that the null hypothesis would say there is no difference between these groups as a result of treatment, that the treatment condition did not work. So the second step then is to create a control group and estimate the population mean when no treatment is given. So the control group stands in for the untreated population. The intervention group stands in for the population of folks who have received the treatment. And again, you want to have large enough samples to be representative of the population. Small samples mean greater error in those estimates. Bigger samples typically do not. And then the fourth step is to compare the means of the two groups once the treatment has been given to the treatment group. If the difference in the means is too large to be due to random chance factors, and we calculate that mathematically based on the standard error, but we're not going to go into that because it's not necessary for this course. Then we would reject the null hypothesis. So rejecting the null hypothesis is a mathematical outcome. Okay, and there are very specific steps that, again, if this was a statistics course, I would walk you through, but I'm not going to do that. But the point is, if we reject the null hypothesis, what we're saying is we believe that there is a relationship between the treatment and the outcome. Okay, that the treated population, for example, in the cancer example, the treated population is in fact showing fewer symptoms, better mortality rates, and so forth than the untreated population. Therefore, the alternative hypothesis, okay, what's not the null, the alternative hypothesis is that as the mean for the treated population on the dependent variable of interest. Okay, so let's just review real quick. I've been throwing out this term statistically significant. I've talked about it within class, but let's make sure we put it on video so you have a chance to review this concept at your leisure as well. It's really important that you understand what we mean by statistical significance. And what we mean in shorthand is that the results make us confident that we should, in fact, reject the null hypothesis. And so what is the null hypothesis? Well, again, we started with the null hypothesis saying there's no difference between the control group and the treatment group at the end of treatment, right? So when we reject the null hypothesis, what that means is we read of a control group and the treatment group in the population. Once we reject the null hypothesis, the only decision-making error that we could make is what's called a type 1 error. Okay, and a type 1 error is when we reject the null hypothesis when it is actually true in the population. This is called a false alarm. So for my cancer treatment example, if I rejected the null hypothesis, what I'm saying is, I think that this cancer treatment does in fact lead to better outcomes. Therefore, I reject the null hypothesis that it's ineffective or that there's no difference with the control group. Now, the error I could be making in that decision is that maybe in my study, in my sample, in fact, the data misled me a little bit. It doesn't mean I made an error in how I ran the experiment. It's just part of the measurement properties in the experiment. And in fact, the cancer treatment doesn't work. In reality, maybe it doesn't work, but my experimental study said that it did. Okay, so when we try to use this drug out in the population, we find that, hey, there's no difference. That would be a type 1 error, okay? And essentially the type 1 error is equal to what we call the alpha rate, which is 0.05. The probability of making a type 1 error is equal to sort of the regions of rejection. But again, information you probably don't need to know to understand the point of a t-test. But what you should understand is when we have a statistically significant t-test result, what that means is we've rejected the null hypothesis. We've rejected the idea that there is no difference between the control group and the intervention group. So we reject the null hypothesis when the probability of the difference between the means being due to chance factors is very low, less than 5 in 100. Okay? Now typically, the lower the p-value, this is something you got to wrap your head around now, the lower the p-value, okay, what that means is a really, really low p-value. Let's say p less than 0.0001, okay? What that means is, the probability that any difference in the means we're observing is due to chance is really, really low. So as an experimenter, I want to see a low p-value, okay? Because I want to reject the null hypothesis. I want statistically significant results because statistically significant results show me a relationship between our intervention and the outcome. So typically, the lower the p-value, right, what that suggests is the greater the effect size. Because if you can imagine, remember those two vertical lines in the distributions we were just looking at? Imagine the blue vertical line moving way out to the right. Well, as it moves farther and farther out to the right, in fact, let me go back here. Imagine that blue line, and it moves out farther and farther to the right, right here. And it goes way out here, and the distribution, the blue distribution goes with it, right? What's happening to the size of this effect? Bigger and bigger. So as we get stronger and stronger treatment effects, we typically see lower and lower p-values, and vice versa. As that p-value gets lower and lower, the treatment effect is going to be higher and higher. Corresponding, and you can do the inverse too. The closer the mean of the treatment is to the mean of the control group, the smaller the effect size. Okay, so I'll skip back through my slides here. Okay, now, if the mean the mean of our treatment group gets really close to the mean of the control group, then we fail to reject the null hypothesis. And what that means is that the p-value is typically larger than 0.05. And the effect size is smaller because the mean of the control group and the mean of the intervention group are now pretty close to one another. At this point, the only decision-making error that we can make is what's called a type 2 error. And a type 2 error results in us failing to reject the null hypothesis when we should have. It's called a miss. Okay, now the probability of making a type 2 error is a lot more difficult to calculate than the probability of making a type 1 error, and I'm not going to go into it here. But you can make type 2 errors for all sorts of reasons. You might have poor measurement instruments. Your samples could be really, really too diverse. You may have a bad sampling strategy. It's a lot of sort of methodological as well as quantitative factors could go into making a type 2 error. And then finally, we have the dependent or matched samples t-test. This was the third one that we talked about. And like I said, its most comparable analog is the AB design, especially when we're going within subjects. It's still a group design because we're studying a sample that is n larger than 1, n greater than 1. It's behavior pre-treatment to post-treatment. Okay, and that would be a dependent t-test, not a matched sample t-test, but a dependent t-test, when we compare samples of each participant's behavior pre-treatment to post-treatment. And here's kind of how it works. So imagine we had 20 participants in a study. What we would do is we would measure each participant on the dependent variable prior to intervention and then after intervention. Okay, so in this case, we don't have a control group where the control group does not receive the intervention. Everybody's getting the intervention. And that's one of the advantages of a dependent t-test is that, let's say we really think that the intervention is going to work, and we would have ethical issues if we didn't use the intervention on everybody. In this kind of design, everybody gets the intervention. Okay, so we collect data before they get it, and then we collect data after they get it. But we create a new kind of score. It's called a D-score, or a difference score. And that difference score we calculate for each participant. And it represents the difference in scores on the dependent variable between pre-test and post-test. We then sum those difference scores across all participants and then determine whether that sum is significantly greater or less than 0. Because if the null hypothesis is true, that the treatment doesn't work, then what we should see is that when you sum those difference scores across all subjects, the sum should be pretty close to 0. It may not be exactly 0, but so close that chance or measurement error could account for any deviation from 0. So the null hypothesis in that case is that the sum of the individual differences should equal to 0. Now, in most experiments, experimenters will use a mix of independent samples, t-test, dependent samples, t-test, just picking one type of test for an experiment or the other. But you're probably going to pick a bunch of them to report in your study. And you need to know, as a consumer of this information, even though you're a behavior analyst, you may not be doing a lot of this, okay, you need to know what these tests do, and then how they're expressed within the research literature. And so that's where we're going next.